All right, well, let's hear from you guys about what we're talking about in class. So we started, all right, David.
We talked about.
Yeah, we'll get to it. Yeah, but liquids are, liquids do increase in density the more pressure they're under. So the water's a little bit denser at the bottom of the ocean than it is at the top. But they're, for all intents and purposes, ideal liquids are incompressible. You certainly don't end up with a situation where you can definitely compress them like you can with gases. Largely because gases are treated as point particles, and so they really don't have an appreciable volume at the atomic level in those equations. So it's a very interesting accounting situation. What do I want to say about that? You know, we've been through some really interesting changes in the past. Did we talk about heat in this class already? The magical fluid of heat? No? It's kind of a cool story. I mean, not that long ago, heat, the equations that govern the flow of heat, they're essentially parallel. I was going to say identical, but they have the same form as the equations that govern the flow of fluids during diffusion. So, if you put a drop of liquid like a dye into a big vat of water or a little beaker, it's going to kind of diffuse and spread out throughout it. And heat moves, it transfers between regions of a fluid or regions of a body in much the same way, and the same equations worked out. And it's so striking that for a very long time, when people started actually doing experiments in the lab and science was kind of being born, people were absolutely convinced that heat was the flow of some sort of fluid throughout bodies. They gave it a name even. It actually had several different names. And that held on for a very, very long time. There was a huge debate at the time as to whether atoms were even a thing, really, also. It was very popular to treat atoms as, instead of atoms, to kind of have these point systems with arrays of vectors that describe the forces that would be present at that point in space. It actually took a gentleman who was working in the army at the time, had been around the artillery system for quite a while, and he was actually thinking about, he was, I think, investigating, he was making some tour of how they built these cannons at some point. And he had the realization that as you bored out the holes in these, they make cannons by essentially drilling a big piece of, some sort of metal, I think it's iron of some sort. They drill out the hole in the cannon to make this tube so you can shoot cannonballs out of it. And the drills that they used would get really hot, and the cannon, what they call the bore, the hole that the cannonballs fly out of, got really hot too. And he had this realization that essentially if you had like an unendingly long cannon, it seemed like you could evince an infinite quantity of this heat fluid from it. So in other words, you could get as much heat as you could continue drilling as long as you had substance. And that didn't really sit well with him, and the way that he ended up writing it up was very compelling to his peers at the time. And, it turns out there was another gentleman working in the wings, this guy named Boltzmann, Ludwig Boltzmann, who had actually prepared an atomic theory for how heat could just be the motion of atoms inside of a material. And, it's a really sad story because Boltzmann was not a very, let's say, he wasn't a man in high esteem. He didn't have a lot of fame in his day. And, his entire platform was built on the assumption of atoms that could do this motion. And atoms were not very popular at that moment. And Boltzmann ended up hanging himself, actually, because he completely lost hope that any of his work would ever amount to anything. And just a few weeks later, actually, this cannon boring experiment was publicized, and the whole theory of how heat flowed as this magical fluid was completely upended, and people embraced the atomic theory and embraced the idea that it was actually just the motion of atoms that was doing this thing. And so, kind of overnight, in some sense, our entire understanding of heat, going from this kind of magical substance that flowed around and was infinitely regenerable, to a very materially plain, mundane, ordinary explanation appeared and stuck with us to this very day. And there's kind of, science is just replete with examples like this. So we are not without precedent in these things. And it should be par for the course. And that's kind of what's cool about science, honestly. It's not meant to be a stick that's planted. It's not meant to be a flag that's planted where we just learn something and that's it forever. We always have to update our understanding as we move forward, despite how nice the mathematics might be, right? So that treating heat as a fluid works perfectly. Mathematically, it's perfect. It just nails it. But it's incongruent with some observations, and so people had to rethink that whole idea. Yeah, all right, let's keep going. Like I said, I want to walk up to the precipice of black holes today. I think that's going to require us to talk a little bit about gravity and general relativity. Black holes are in some sense not only permitted by gaseous stars, but they're also in some sense permitted by the construction of space-time, which is a really interesting concept that we need to make sense of. So let's see if we can make it there. I have a few more things I want to follow up on with regard to the different stories of the end of a star's life. We need to talk a little bit about supernova first for a second. So now, remember, we basically have two parallel stories going on here. We have a story that we tell if our stars are in a liquid state, one if our stars are in a gaseous state. The gaseous story essentially involves the depletion of fuel at the core of stars. Remember, in the gaseous stars, all of the furnace of fusion is only at the core, where the temperatures, due to pressure from gravitation, are great enough that you can actually fuse these atoms together. In the liquid model, things are a little bit different. You have the ability for these fusion processes to happen between layers, potentially throughout the star, not necessarily at the core. And you don't really have this situation that you do in the gaseous stars, where once you use up fuel at the center in the gaseous star, there's nothing to push back against the weight of gravity. The star kind of crunches down on itself. And depending on how big the star is in the gaseous model, you're going to be able to use that additional pressure of the collapse to do new kinds of fusion. And that works up to a point, say something like iron really being the bottom of the barrel there. At which point you have a really destabilized structure for your star, and it essentially dies a violent death at that point, right? It's either casting off layers in the form of a planetary nebula we talked about. We looked at some pictures of it. Or for a really massive star, we end up with something called a supernova. In the liquid model, it's not too different. The main difference is that you have the potential for the intercalation of these fusion substrates, which could potentially lead to little bubbles in between the layers of the liquid metallic hydrogen lattice, and you have this exfoliation of layers. The product is the same in both cases. Depending on how big you are, you might end up as a red giant swelling and giving off layers, or you could end up with something catastrophic like a supernova that we're going to talk about. Okay. I thought I was going to talk about this, but I'm not. In either case, we have our HR diagram, our luminosity versus temperature, and we have this precession of the star as it kind of makes its way off the main sequence, and finds its way down in the white dwarf space over there on the bottom left of the diagram. Now, in the gaseous model, every single star has to die this way in some sense. Every star needs to leave the main sequence, go through a giant phase, and then it needs to shed its layers, or it needs to explode violently in a supernova and collapse. Its core collapses down into this ultra-dense object called a white dwarf. With the liquid stars, this is more of an anomalous situation where some stars become unable to expel their fusion products from the lattice properly, and it's catastrophic. Maybe they lose layers, maybe the whole star gets blown apart. But it's a much more rare process. Most stars in the liquid model are just going to drift down the main sequence as they get rid of all of their material and their solar wind and so forth. They're going to cool off, and the result of them cooling off is eventually something like a brown dwarf, like Jupiter. It's essentially going to be a hydrogen ball that's not hot enough to do fusion anymore. Now, there's actually a road in the gaseous model too for something like this. It's called a black dwarf, and this basic idea is that certain white dwarfs, actually all white dwarfs eventually, will radiate away all of their heat into space, and those white dwarfs will eventually cool off themselves. And once they cool off, they're just going to be these kind of moon-like objects that are very like carbonaceous and just sort of burnt up rocks. Now that's thought to take forever, I think certainly on the order of billions of years, if not trillions of years. So if the universe is believed to only be 14 billion years old, it hasn't been long enough for any of these white dwarfs to convert into black dwarfs. However, like I think I mentioned to you guys last time, I wanted to show you some pictures. So really cool study called VASCO that found all of these disappearing stars in the sky when they looked at these frames across about 30 to 50 years back during the 20th century. And it's very, very interesting and compelling stuff. The authors were not able to guarantee that what they were looking at were actually stars. They tried to rule out as many things as they could. But it does seem like some of these things that we would call stars in the sky, these pinpricks of light, have disappeared over the years. And the number of stars that occupy, say, the giant phase on the HR diagram or the dwarf phase on the HR diagram is really small, actually. And the number of supernovas that we've seen is even smaller. In fact, we haven't seen a supernova in our own galaxy since Galileo's time, which is kind of bizarre if this is kind of the route that stars need to take. So actually, I kind of pulled this diagram from actually a Scientific American article from a few years back, where they're actually talking about the very fine difference between a star and a brown dwarf, and how, this is kind of working off of my thought experiment that, you really just have a matter of one atom being packed into that space at some point. There's a fine line between when you have enough mass in one place to do fusion. So it doesn't seem inconceivable to me, liquid or gas, that your star at some point may lose that atom or gain that atom, and it may go into that bright mode, it may lose that bright mode, right? So that's an interesting piece of thought right there. And naturally, of course, you can fit brown dwarfs onto the main sequence if you extend it off into the distance. So we usually only see this top this top side of the HR diagram, but you certainly could fit brown dwarfs onto it. They're not doing fusion, but they fit really nicely onto the luminosity temperature graph. Of course, now you're out in the infrared range, so you're only really seeing this kind of microwave, radio wave, infrared radiation. They're not glowing in the visible range anymore. Okay. Thoughts, questions, anybody? All right. Okay, so like I was saying, we kind of last time gripped the standard story, I hope, of the ultra-compact object collapse in the case of the gaseous stars becoming white dwarfs. If the things are big enough, that iron core, which is remnant as these stars have cast off their outer layers, it gets so big that even the white dwarf itself can't support itself anymore. Now, the density at this point is the theoretical density that's necessary is something like 400 billion times as dense as water. So we're moving into, 400 billion, again, it's a billion is 1,000 million, a million is 1,000,000. You're talking about something whose density is absolutely unimaginable. So anyways, at this point, when, in theory, these stars, these gaseous objects, have reached this level of density, they can't support themselves anymore, and their atoms themselves actually collapse upon one another. It's no longer to even keep charges separate, which is a whole other matter in terms of what that even means. But the thing collapses down, and we call it a neutron star. So, and it's theorized that this actual ball of crushed down neutrons is actually stable for long periods of time. And the result of that, what happens when this core collapse happens in this final stage for these really massive stars, is that a tremendous amount of energy is given off in the form of neutrinos, which are kind of a weird. Neutrinos are a weird thing. They were actually entirely theoretical when I was a kid. They set up these huge detectors, I think, in the side of mountains and these huge water tanks, and eventually were able to detect these. They're kind of like light in the sense that they radiate away from stars and so forth. They're very, very energetic particles. In some sense, they're thought to penetrate directly through matter. Another way might be just that they're losslessly relayed through matter, no problem. But there's a tremendous amount of neutrinos that are released in this gaseous collapse for this model. Something like 10 to the 46th watts of energy, which is more energy than all of the other stars in billions of galaxies have put out to this very moment, given the lifetime of the universe. So it's an unimaginable amount of energy that results from this. And the thought is that this is the energy which propels our supernova. It's actually called a type 2 supernova in this case. We'll talk about type 1s later. So this is interesting because using this model, we have finally the amount of energy that we need in order to slam things together in order to make some of these really heavy things that we see in the universe, but we're not able to produce using this model of fusion at the heart of stars, or even at the heart of collapsed cores like white dwarfs and so forth. We need even more energy to pull off some of these huge atoms, these big, heavy atoms. And we get that from these supernovas, which is pretty cool. And in either case, certainly supernovas contain a great deal of interesting metals that we don't see otherwise. We can see supernovas in other galaxies too. So I mentioned we haven't seen one in our galaxy in a very long time. This is true. We do see supernova in other galaxies, and they oftentimes are so energetic and bright that they outshine the entire galaxy. So the whole galaxy is dimmer than the supernova itself, which is pretty extraordinary. Here's a few pictures. I think these might be from your textbook. So, these are, of course, since they're billions of light years away, they're thought to have occurred a long time in the past. But basic idea, just to kind of contrast these two things. The white dwarfs are actual... Oh, in the back, yeah.
I think this is slide that they can see. That's what like the neutron star black hole.
Yeah, it's all about, so, neutron stars, black holes, under the gaseous model, they all depend on the amount of material that's there, right? Under the liquid model, those appearances are more anomalous. They probably result from different, almost like from different chemistries inside of the star, if you can think of it that way. You may have a star that has it has fusion products that are not sustainable. Perhaps it's been involved in some. So, okay, under the liquid model, you gotta think about stuff like metastability really carefully. Have you guys ever heard of like super-cooled liquids before? You ever done this experiment like where you freeze like a water bottle in the freezer and pull it out and it's still liquid, and then you tap on it and it just turns to ice really quickly? Right? So metastability is a really weird concept. And it's actually really common throughout our universe. It's actually common in your daily lives too. There's forms of matter that'll be in one phase, and then if they're disturbed in any way, now it could be electrically disturbed, it could be mechanically disturbed, like tapping on that water bottle, or it could just be subject to heat and temperatures and so forth that can cause this snap between phases that are extended way beyond where they're supposed to be in their phase diagram. the thought is that in the liquid model, you may have situations like this, where you have pockets of fusion products in layers, in the onion layers of the star, that are metastably bound. They're maybe in the solid phase, for instance, and they're only metastable in that solid phase. But if the star was to experience, I don't know, a passing star, maybe it gets hit by a comet, I mean, anything that could disturb it, maybe it has some electrical process that disturbs it. You could have the rapid expansion of layers inside of it that would result in something catastrophic. So you end up altering that. You alter the lattice state of the star. You're also going to alter its optical properties. So actually, diamonds are a metastable state of carbon, for what it's worth. If you just took a diamond and set it on the table for millions of years, it would turn back into something like graphene eventually. So, which obviously has very different properties, as I've beaten this horse over the head all course long. Diamond and carbon, again. Diamond and soot, diamond and graphene. They're both 100% carbon. They just have different lattice arrangements, very, very different optical properties. So again, under that model, these things, these black holes, these white dwarfs, these neutron stars, they're not necessarily not made out of hydrogen. They could be ordinary composition stars like hydrogen. They just have a very different lattice structure, which gives their appearance of being very dim, but remaining quite hot at the same time. So, very different models. But of course, under the gaseous model, it's all about mass. The more mass you have, the more you can compactify that object. And of course, all of these objects result based on more and more compact objects, the black hole being the most compact of all. It technically has a radius of 0, so I don't know how you get much more compact than that. It's hard to even understand what that means, actually. We'll deal with it, though. Don't worry. So there's something kind of interesting. So when we talk about what can we actually see, so when we can see visibly some light still coming from a little place in the sky where there's some gravitational business happening, it might be a star, an ordinary main sequence star is orbiting a point, and we look, what is it orbiting? If we can see what it's orbiting with visible light, we generally call it a white dwarf. If we can't see it, but it's emitting the proper, let's say, fingerprints of radio waves and X-rays, we might call it a neutron star. And if it's really, really dark, we'll end up calling it a black hole. So, well, those are kind of the delineations there. What else can we say about that? Okay, so these supernovae are pretty cool. I think I was kind of talking to you guys about how different elements can be generated because there's enormous energy that's available in these explosions. And it's pretty cool. So the expanding shells, we see these mostly in other galaxies, like I said, entirely in other galaxies. And these shells, as they expand, they contain all of the elements that we've been looking for, a lot of the really heavy ones, right? So it's pretty cool. And a lot of them are radioactive, so it indicates that they were formed very recently in some sense because, you know, they're not going to be around very long, radioactive elements. So let's see here. This is a good illustration of that. So what we're looking at here is actually different forms of radioactive nickel and iron that are in the expanding shell of one of these supernova, which is pretty cool because we've finally reached a point where we've generated the basic stuff that we find under our feet. Remember, this Earth, its core is this nickel iron core. Those are really, really heavy substances, really dense substances. And so in some sense, we've got a guaranteed ability to make precursors for some of these rocky planets as well. I know we've been flirting with a lot of different ways that you could generate planets, particularly the rocky planets, which I think are the most mysterious of all because they're so freaking dense. They're 5 times as dense, our planet anyways, is 5 times as dense as the sun. It's pretty wild. So how do you make one of those? Well, you certainly have a lot of those starting materials that pop out of these supernova explosions, and that's pretty cool. So in either case, liquid or gas, you have a bunch of building blocks released after these explosions, which is pretty wild. All right. So this is kind of cool too. There's this interesting phenomena that was discovered actually in '67 by an astrophysicist named Jocelyn Bell, who was working on some of the early radio telescopes. And she essentially discovered this oscillating signal that was coming from what was eventually deemed to be a point with gravitational interactions that didn't appear to have any visible source associated with it. So it was deemed to be a neutron star on the basis of the fingerprint of the radiation that was coming out of it. And the interesting thing about the radio signals coming from this point was that they oscillated. So it was kind of making this chirping sound. If you can convert radio light into a sound, it was basically this low frequency oscillation. And the theory was that the star was actually spinning extremely fast. Of course, it's unbelievably dense under this gaseous model, and so you have tremendous amounts of energy available once the thing gets moving. So the thought was that pulsars were actually directing this light, particularly radio waves, and to a lesser extent, X-rays, gamma rays, off at their poles. And the poles, as they were flipping around, were making this beautiful pattern. They actually called them, the radio astronomers called them LGM originally, which stands for Little Green Men, because they thought maybe this is some alien Morse code stuff going on. Maybe it is. I don't know. Nobody really thinks that too much these days, but it's an interesting hypothesis. There's an interesting way too. So of course, as with every piece of this class, there's a buzzkill with the liquid model, because with the liquid model, you need to have a flashing radio source as well. Turns out that we have a really convenient one here on Earth, which you guys are probably very well acquainted with. It's called turn signals. The technical name for a turn signal is a relaxation oscillator. It's basically a simple resistor capacitor circuit where you sort of charge up the circuit, and the capacitor builds up this charge. Once it reaches a certain point, it overcomes the resistance of some resistor, which discharges the capacitor, and then the whole thing kind of oscillates and builds up again. So it's conceivable, that depending on the actual lattice arrangement of the material, as the lattice oscillates in its conformation, you would actually have different conductive properties. Remember, diamonds are electrically insulating. You cannot connect a circuit with diamonds, but they're made out of carbon. Graphene is a great conductor, actually. So you can make a circuit out of graphene. And so just by changing the arrangement of the atoms, same density, everything is the same, just by changing the structure of that crystal, you end up with wildly different conductive properties. And so you also, of course, end up with wildly different optical properties. So that's a hypothesis for you, too. Turn signals. All right. So we've talked about how a single star might nova in both the gaseous model, the liquid model. We haven't talked much about binary systems, though, and we definitely realized that most stars seem to have partners, if not, what would you say? What's the three, four quartets, right? Most stars have partners, right? So there's a different process that's theorized to occur when you have partners, right? And in the case of partners, the idea is that this kind of process of building up mass and collapsing could happen much faster. So if you're an ultra-dense white dwarf star under the gaseous model, and you're sitting next to a regular main sequence star, you've got all that gravity, and you can just kind of put your gravitational straw into the other milkshake and take all of the material off of that partner star and condense it really fast. And it's going to kind of accelerate your timetable for how fast you're going to collapse on yourself and result in some catastrophic explosion of some sort, or fast forward to neutron star or black hole. So this is entirely theoretical. No one's ever actually seen this happen, but it is a different process to reach a supernova, and we call the supernovas that result from this kind of process type 1 supernova. The first ones I told you about were type 2. I know it's out of order, but the type 2s are easier to comprehend because they happen in isolation. The star doesn't need to accrete somebody else's material to make it happen. So the serious difference between those two is that in the case of the type 2s, it's going to happen much faster. In the case of the type 1s, I actually had that backwards. I do apologize. The type 1s, it seems, are actually going to happen much slower, which I will have to get back to you guys on. I apologize for that. I had it backwards. What's kind of interesting is that as these things are creating this material, the models allow for this to actually lead to that pulsing phenomena, that rapid spinning process that we talked about before. So as we discussed the figure skater in the past, who's kind of moving inward like this, the same thing could be said to account for this pulsar activity if indeed these ultra-dense objects are spinning truly fast and not doing the turn signal thing, like I pointed out earlier. Okay, so we're getting very close to being able to examine this gravitational collapse program a bit, because obviously this idea that some material is going to collapse on itself to the point of having almost no radius or no radius at all, it stretches the imagination, and we need to understand why in the world people have theorized that this is the case. I think in order to do that, we have to understand relativity a little bit. And relativity is a little bit perplexing in some sense, but I think we have to set the stage for it at least. So for most of the history of science, we had defaulted to Newton's laws of gravitation, the very simple ones we built out at the beginning of this course. We essentially say that the attraction between different bodies is really just a product of their masses. So in other words, how many atoms and how big those atoms are. And it's split by the distance between them, squared. So if you have bodies that are separated pretty far, there's not much attraction. If they're really close together, there's a lot of attraction. That was sufficient to explain most phenomena for most of the history of science. There started to be some rethinking about how all of this would work. Now, there's kind of two paths to go about understanding why in the world people were looking for something better than that. One of them was that Newton, when he wrote these gravitational laws in probably the most famous science book of all time, it was called Principia, he kind of obsessively came back and was always writing little addendums to the book as new editions were released. And in one of those addendums, he basically went on this kind of self-loathing apology about, how he didn't really know what caused gravity. And I think it was driving him mad. And he went so far as to essentially say that not only do I not know what causes gravity, but nobody should try to figure it out. It's not the job of scientists to figure out what causes things. It's our job to write equations that are accurate and tell us how things happen. Now, that's an interesting, that might just come off as like a cranky guy at the end of his career who hasn't figured something out. But Newton was something of a god in his day, and actually he kind of still is. He was thought to be the smartest man who ever lived, even while he was alive. People took him really seriously when he said these kind of things, and the downstream history of the story played out very much in accordance with that. So people would study people in some sense in the back of their minds assumed that there was something in between the planets that was conveying this force of gravity. There was some kind of medium, and we've touched on it before when we talked about electricity and magnetism and all of this. They assumed that there was an ether of some sort. And so eventually, like maybe 130 years ago, 150, not even 150 years ago, people set out to really look for that ether. They said, you know what, we've always kind of assumed it's there. Newton said don't worry about it, but we really want to find it, because if we did, that'd be nice, and we could lay to rest the cause of gravity. We know how gravity operates. Let's see if we can figure out what is actually doing all that pulling in between the bodies. So they go looking for it. And lots of different labs on both sides of the pond were trying to figure out how we could detect this ether. And nobody was able to do it. Nobody. There were some reports of there being some presence detected of the ether, but they were not the same as other reports. There was basically no consensus available about this. Now, shortly thereafter, there was a rising star in physics, and I'm sure you guys have all had his poster on your high school physics wall. But this is Albert Einstein, right? Comes along. He actually gains a lot of fame working off the idea that light needs to be quantized, and then develops this idea that you can shine light on metals and develop electricity as a result of it. He also gains a great deal of fame. He ends up getting a Nobel Prize for his work on atomic theory, the very matter that Boltzmann ended up hanging himself over, where he basically shows that atoms undergoing heat will wander around kind of randomly as a result of it. It's called Brownian motion. So anyways, Einstein's kind of a rising star. And he sets himself on the task of trying to solve a tangential problem, which is Mercury's orbit. Mercury is kind of weird. So all the planets in Newton's solar system more or less do the nice thing that Newton had refined that they should do and defined in his equations. Mercury was a little bit weird. So not only does Mercury orbit the sun with this nice particular elliptical orbit, but that elliptical orbit itself is kind of rotating. This is called the precession of Mercury's orbit, right? Or the precession of Mercury's perihelion, which is its approach. And so this was odd, and people couldn't make sense of it. And Einstein, in some sense, set himself on solving this problem. Simultaneously, he wanted to prepare a way of looking at reality that took out the messy problem of having to have a mediator for gravity, right? So in tackling both of these problems, he ended up preparing a new mathematics for how we approach the motions of bodies in the solar system. And the way that he developed that mathematics is actually extraordinarily simple and really brilliant. He basically had this idea that two seemingly unrelated ideas, which is inertia and gravity, were basically two sides of the same coin. Now, what does that mean? Well, it means that what is it like? Let's talk about some inertial systems, right? So the classic thought experiment is you're in an elevator, right? And somebody just cuts the cable on the elevator, right? So you start falling. Well, it's interesting because your experience in the elevator as you're falling is that you're basically floating in the middle of the elevator. It basically feels like somebody turned the gravity off, right? So what Einstein did was he essentially put Newton's representation of inertial motion, this F equals ma thing that you guys all learned about in high school physics, he sets it equal to his gravitational equation and develops, using some of the highly sophisticated maths of the day, develops a way to parameterize bodies in space using this basic concept that inertia and gravity are the same thing. Now, he may have taken that idea from this other dude named Ernst Mach, who wrote about it tangentially and never really developed any mathematics for it. But Mach seems to have had the notion that gravity resulted from the same processes as inertia. He actually had this really interesting thought experiment where he was like, why is it that when you spin your arms around, why is it that when you spin your body around, your arms fly off to the sides? Like, what is up with that? because it doesn't totally make sense that that should happen. And it seems that it doesn't really depend on your location with respect to altitude either. It doesn't seem to be directly related to gravity all by itself. And he had this kind of crazy idea that, well, it might be because your arms are connected to everything around them in some invisible fashion. In other words, that even the distant stars and the whole universe was conspiring to keep your state of motion held in place. And so Einstein maybe picked up on Mach's ideas and worked out this equivalence principle for inertia and gravity. Anyways, long story short, Einstein develops a way of parameterizing the motions of bodies that doesn't involve any mediators whatsoever because he comes up with this idea of space-time. Now, space-time is an interesting concept because it sounds a lot like some sort of substance, right? It sounds like some sort of goop. It's not quite that, and I'm going to come back to that because what relativity actually does is it takes into account all of the perspectives of every observer possible when relating a phenomenon. So I like to use this example, although I'm kind of stealing it in some part from this paper called 111 Years of Magic. What is this called? Are Enough. Fantastic paper by a Greek philosopher. Let's say, I'll make you an analogy for the way that relativity works. It's like this. You walk into a theater, and it's a theater in the round, and we're watching Peter Pan, right? And Peter Pan flies in from off the stage, and then does something, and the play unfolds, and you go to every audience member and you reconstruct their perspective of the event, right? So everybody sees something a little bit differently. One person, sees Peter Pan flying from this angle. Somebody else, depending on where they're sitting, they see it from the rear. And you reconstruct mathematically all of these perspectives of what Peter Pan looked like flying in off the stage. You have a very, very accurate description of that phenomenon as a result of engaging in all of these different perspectives at once. This is essentially what relativity is doing, actually. It's examining all of the perspectives, and it's created a very complex three-dimensional mathematics, actually four-dimensional because you're adding in time, so you're talking about the motion of Peter Pan at the same time, basically making a movie from everybody's perspective of what happens. So what happens is you take this essentially you can almost think of it as a 3D simulation of what happened when Peter Pan flew onto the stage, and you walk out and you say, well, what happened in there? And everybody looks at this meta movie of what's happened and they say, well, the actor flew in off the side, landed on the stage, did some stuff, and flew away, right? Well, it's interesting because that is technically true about what happened. But the funny thing is that the parameterization didn't account for the little strings of cable that were attached to the actor as the actor came into the stage, right? So while relativity gives us a great amount of power for describing what's apparent, what's visible, what we can see, it doesn't necessarily reveal anything mechanistic about what's happening behind the scenes. Another way you might be thinking about it, if there's somebody on stage, like it's an illusionist show, and you see this magician sawing this woman in half on the stage, right? And you reconstruct the audience's perspectives of what's happening. They're all going to say, the lady got sawed in half, right? But nobody could see inside the box, and inside the box is where all the magic is happening because the lady just picks her feet up and doesn't get sawed in half, right? Those are things that you can't account for from external perspectives alone. And so what relativity did was give us an extremely precise improvement on the way that these bodies seem to interact with one another gravitationally. And I think that it really did flow from a brilliant observation that inertia and gravity were two sides of the same coin. Now, the annoying thing about it is that it does make a parameterization of the system in terms of two concepts that we've discussed loosely so far. One is space, which is essentially a coordinate system of locations. And the other one is time, which is essentially a comparison of motions, right? So if you think about what does a clock do? Well, it has a repetitive motion that you treat as a standard by which you can gauge any other motion by, right? That's why we time races with clocks and so forth. So what happened is that over the course of the next 100 years, in the wake of Einstein, people began to treat this space-time concept as if it was an actual substance. I think even your textbook starts treating it like a substance at some point, and applying these physical transformations to it, like warping and so forth. But of course, it's not. It's really just a measurement system, a coordinate system for grasping the location and dynamics of the motion of these bodies. So, here we have the warping of space-time. Time's a really, really interesting one too, because it's really, really tempting to treat these ideas as if they are substances that we can apply these physical transformations to. I'll give you a good example, right? So one of the consequences of general relativity is the way that gravitational systems affect clocks, which is really, really fascinating. Now, in a physics equation, when you see a little t that stands for time, what do you think they mean by that? What's time in a physics equation? Anybody? Yeah, step out on a limb. You got it.
The amount of space in between you're starting a thing and then
You're on the right path. Anybody? Yeah, so time's just what clocks do, actually, is what it comes down to, which is a little bit of a letdown. So it is and it isn't, though, but things start to make a lot more sense. So there's this really famous experiment that was done, kind of accidentally, actually. I believe there's a satellite in orbit not too long ago. This is maybe 30, 40 years ago at this point. And the satellite was like a little bit broken, like one of its jets didn't fire right or something. And it entered into this highly elliptical orbit with the Earth. So it would, at some approach, it would become very close to the Earth, and then it would be kind of far away from the Earth in its orbit. And it just so happened that this satellite contains a clock, a really precise clock called an atomic clock on it. And so the scientists were astounded to realize that the clock was actually slowing down when it got close to the Earth. And it did it exactly with the precision that Einstein essentially prescribed that it would happen. And so everybody lost their minds and they were like, wow, time slows down in a gravitational field of some sort. Now, what is time again? Time is what clocks do. Here's the thing. The way that an atomic clock works is that the atomic clock is essentially measuring the standing wave light pulses that are given off by some kind of atom. I believe these were cesium atoms, some sort of metal, heavy metal. So the light is this has a very periodic motion that you can use as a clock. It's giving off some wavelength of light that's very consistent. And what happened was that wavelength got longer, the frequency got slower as it came into contact with the Earth's gravitational field. That's not particularly spooky or supernatural or anything else, because why shouldn't a clock be affected by being in the presence of other atoms? If the atoms are indeed experiencing the pull of their neighbors through whatever structural arrangements that you can imagine, and we've talked about a few at the beginning of this class, but if atoms do have a kind of continuous structure to them such that they don't end at their shell, but their shell is kind of fuzzy in a way, and they are able to contact their neighbors and apply tension like gravity to one another, well, then the more of them that are around, the more tension should be exerted on those atoms, and in effect, what you would have is a damping effect on those atoms. Of course, their breath rate is going to slow down, and of course, their light is going to reflect that. So, another good example might be like, hey, what happens? Anybody have a grandfather clock in their house that their parents do? No? You guys never been around grandfather clocks? You got one. Parents have one? My wife's family has one. It's super, super obnoxious when you're trying to sleep and stuff. Grandfather clocks work on a pendulum, which is another periodic motion that's capable of clocking things, right? It's very predictable. It takes the same length of time for this pendulum to go down. But what happens if you take a pendulum clock say, up to the space station? Well, time's going to stop, obviously, right? So you have to be really careful with clocks, because clocks are often going to reflect much more about the construction of the clock than anything else. Certainly gravitational systems are going to affect how atoms behave. But the concept time, the reason I bring up the grandfather clock is I want you guys to understand the concept of time, the comparison of a periodic motion versus some other motion. That's just an idea. Ideas are not subject to physical processes. You can't warp an idea and you can't move ideas around the room. I can't ask you guys to hand me some love or something, right? I can't take an idea. I can't twist the love for my wife into a ball and throw it in the basketball hoop. Like, these are poetic, perhaps, but they have no place in physics because we're mixing metaphors at that point. So, anyways, I have a few minutes here, and I want to talk maybe about one last little piece of the puzzle here so that we're all teed up to deal with black holes on Tuesday. And that is the bending of light. So another prediction, if you want to call it that, and I think that's maybe the right term, of Einstein's relativity is that large objects should be able to affect the path of light as well. Now, this is often heralded as the real triumph of, like, the first time that people tested out Einstein's ideas and actually jumped up and down because they turned out to be true. So the story I told you about the GPS satellite and so forth, that was done relatively recently. I think that was in the 80s. And pretty early on, the father of the gaseous sun, let's say, Arthur Eddington, he also was a huge champion of Einstein's work. He was, Einstein was German. The Germans were not popular with the West back in Einstein's day. Arthur Eddington translated his work to English. He really kind of brought Einstein into the West. Eddington also took Einstein's idea and decided he would go test it out. So he traveled. He actually sent 2 different teams to go and watch a solar eclipse at different points on the globe when it was happening. And they figured that they could see the positions of stars as they were, in the line of sight of the sun for the first time. In other words, as the stars were blocked out by the moon, the sun was blocked out by the moon, and the stars came very close to the limb of the sun, that the position of that light should be altered a little bit, according to Einstein's theory. So they did this work, and lo and behold, they actually saw this effect. The positions of the stars did tend to be relocated in accordance with, at least the nearby stars to the sun did seem to have a new location. Now, this was it was a pretty crummy experiment, actually. The accuracy in their measurements was like on the order of 20%, which would never even make it into a low-tier journal today. But people repeated it over the years, and they found this to be absolutely stunningly accurate. So I'm going to skip that. Okay, so actually I'm not. Now, there's another possibility with this as well, which is worth considering. And this work was done by a gentleman, a NASA laser optics physicist who unfortunately passed away recently. I would have loved to have talked to this gentleman. His name is Edward Dowdy. But he brought up some interesting points before he died about the lensing of light near this thing we would call gravitational lensing, which is going to play into our black hole discussion on Tuesday. He noted that there's some problems with this. One is that if this gravitational body like the sun was actually lensing the light according to gravity, that because gravity falls off with an inverse square of distance, that the lensing should also fall off with this same rate. Unfortunately, it doesn't seem to be the case. In fact, the only lensing that's ever been observed with our own star happens only within, I have the number here, essentially only within the coronal area of the sun itself. So when you try to essentially apply this Gaussian smoothing that you should get showing where the lensing should be taking place, you should see it out to several solar radii from the star itself, and we've never seen that. He also brings up the fact that we're supposed to have this enormously massive object at the center of our own galaxy, which we'll talk about is actually a black hole called Sagittarius A. Because it's so massive, I don't even have a number here for how massive it is, we should see an incredible amount of lensing as a result of its mass. And there's no lensing observed for Sagittarius A. And then he also points out that there's these little rings that we sometimes get on the Hubble Deep Field where we see what are actually now called Einstein rings, which are purported to be gravitational lensing around individual stars. But it's kind of bizarre because there's plenty of stars that are collinearly aligned with massive objects like galaxies and so forth that have no lensing whatsoever. In fact, it seems to be a kind of anomalous process that doesn't quite seem to play out in many cases. So anyways, Dowdy, this laser physicist at NASA, he argues that it's actually more to do with the atmospheres of the stars that are providing this lensing and not actually the gravity itself. So there is some dissent in the ranks as to whether this is actually even a phenomenon that has anything to do with gravity at all. Okay, so we've talked about space-time, we've talked about gravitational lensing, we have talked about the death of stars, the collapse of stars. I think we are pretty much teed up to do everybody's favorite subject, the black holes of doom. Yep. Any questions at this point before we go there? You guys need to drink some coffee before class next time. This is getting rough. All right. Have a good weekend, guys. Get some sleep, and we'll do it all again on Tuesday.